Hello and welcome to our lesson on troubleshooting. So far in this course, we have focused on building, installing the cluster and deploying workload and configuring network and storage. But as many administrator knows, establishing a cluster is one thing and making sure that it stay operational and completely different is a challenge. As a cluster administrator, you will be making sure that the cluster stay functional. Your troubleshooting skills must be sharp so that you can quickly identify the root cause of issue and fix it. All of the domain, the troubleshooting section has the highest value. So it's critical to understand the failure scenarios and how to fix them. Before we can troubleshoot a failure, we must first able to see what's happening. This lesson is the foundation for all troubleshooting, monitoring, and logging. Evaluating cluster and node logging. A real-world Kubernetes cluster manages hundreds or even thousands of pods. For every pod, you have at least one container, and every containerized process can produce log output to its standard output or standard error streams. It's absolutely imperative to capture this log output to proficiently determine the root cause of an application error. Moreover, the cluster component themselves, like scheduler or kubelet, produce their own diagnostic log. Kubernetes logging mechanism is crucial for tracking down errors. We can break our logging strategy down into two main levels: cluster logging and node logging. First, cluster logging. Cluster level logging is a big picture solution. Its goal to collect all logs from all nodes and applications and send them to the central external logging backend where they can be stored, scratched, or analyzed. Kubernetes doesn't provide a single native solution for this. Instead, it supports few common patterns. First and most common is node level logging agent. In this approach, you run a special agent like FluentD, FluentBit, FileBit, or Splunk Forwarder, or in case of you are using Lookie, you can use Promptail on every single node in your cluster. The easiest way to do this is by deploying the daemon set. This agent job is to find the logs file of the container runtime, create on node, read them, and then ship them off to your logging backend. The biggest benefit of this approach is that it's completely transparent to your application. Your developer don't have to change their code at all. They just write the standard output and an agent take care of that rest. Your developer don't have to change their code at all. They just write the standard output and an agent take care of that the rest. The second approach is using sidecar container. With this pattern, you add a second container to application pod. The main application container might write its log to a shared mtdir volume, and your sidecar container only job is to read those logs from the volume and stream them to the logging backend. The benefit here is flexibility. You can have multiple sidecar for different log streams. For example, one for access log and another one for error log. You can also use it if your application can't just write to standard output and insist on writing to a file. The third approach is to push logs directly from the application. In this model, the application code itself is responsible for sending its log to its backend. It has its own logging library and connects directly to your logging service. While this is architecturally simple, there is no middleman. It's very inflexible. If your logging backend ever changes, you have to change your application code and redeploy it. Or in some cases, if your application crash, you might lose the crash log because the driver is dependent on the code execution. Okay. Node logging. Node logging. Now let's talk about the node logging. This is about what's happening on the node itself and its mechanism that power the kubectl logs command. When your container runs, the container runtime, like containerd or Docker, redirect its standard output and a standard error stream. It uses a logging driver to write these streams to a log file on a node, typically somewhere in the var log directory. When you, the user, run kubectl logs my pod, the request goes to the API server, then to the kubelet on the node where the pod is running. The kubelet then reads directly from that log file and stream that content back to you. This leads to an obvious problem. What happens if a pod very chatty and writes gigabyte of logs? It could fill up the node disk. To prevent this, you must implement log rotation. This is automated process, often using a Linux tool like logrotate, which will compress, move, delete, or archive log file once they get beyond a certain size of the age. The kubectl logs command will only show you the current log file, not the archived ones. The runtime in our case containerd is rotating stderr and stdout logs automatically. You can change the default configuration to keep order logs, but your recommendation is to stream the logs directly to a centralized location like elkstack or grafana look. Components that run in a container like kubescheduler and kubeproxy are handled just like any other application. Their logs are captured by the container runtime. Components that run as a system service like kubelet and container runtime itself are handled differently. If your node uses systemd, their logs will be written to the journald, and you can read them with journalctl. If not, they will write their own log to the file varlog. I'll connect to my worker node and I'm using journalctl to get the logs from the kubelet service. I'm using -u kubelet service, which means that its unit file name is kubelet and F is for following the logs. So as you can see, it's kubelet log. It's showing me that the container removed at some point. So if anything happens to the containers on the node, like deleting, creating, the kubectl capture those logs. But it depends on your log severity. So you can always change the severity for the log to get more details or less detail on the kubelet. Let's switch back to the slides. Monitoring cluster component and applications. Logging tells us what happened after a failure. Monitoring tells us how our cluster is behaving right now. As an administrator, you need to understand resource consumption's pattern. How many nodes are healthy? What is their CPU and memory usage? Which pods are top consumers of resources? This responsibility falls with the metrics servers. The metric server is cluster-wide aggregator of resources usage data. It's very simple but critical add-on. Here how it works. The kubelet on every node already collect basic performance metrics for itself and its pods like CPU, memory, and etc. The metric server periodically scraps its data from every kubelet. It then aggregates all these data stored in memory, providing a single cluster-wide view of resources consumptions. The key things to know is that the metric server is not historical database. It only knows what's happening right now. If you need to see what your CPU usage was last Tuesday, like the CPU thread, you need a full-fledged software like Prometheus. For a more detailed insight into networking, application performance, disk I/O, or even custom metrics from your application, such as database, a proper metric system is essential. This could be stacked like Prometheus or horizontally scalable solution like Victoria Metrics. These systems provide high-performance querying and aggregation of metrics collected from across your infrastructure. For example, to detect disk pressure before a system crash, you need to use a monitoring solution like Prometheus, which can collect and alert on disk-related metrics. The Kubernetes metric service only tracks CPU and memory usage, so it cannot detect or alert you about the disk utilization or I/O issues. The topic of monitoring and logging is extensive and deserves its own dedicated course. In this course, however, we will focus on using metric server to quickly detect ongoing issues. One of the most useful troubleshooting command you have is kubectl top. This command gives you a real-time top view of your cluster resource usage. You can check the overall health of your nodes. Let me switch to the terminal. So I'm going to connect to the master node, which is 200. And here I can use kubectl top. As you can see, here we have two options. One is for node and another one is for pod. If I'm using pod just without any flag, it's just showing me that there is no pod in default namespace. But like any other Kubernetes command, if I'm using -a, it means that all namespaces, I'll get the current usage, CPU usage, and memory usage by the container. And for the nodes, I can just use ktop node, and you can see the current CPU usage and memory usage on the node. I can also check the node separately, like just control plane node. And you can see right now we have the 6% CPU usage on control plane. Conclusion, our troubleshooting toolkit. So let's review. We have our fundamental toolkit for troubleshooting. We understand how logging works at both the cluster and node level. And we know that kubectl log is our tool for reading the log and from the specific pod. We understand that metric server is in a cluster aggregator for resources data, and kubectl top is the tool for seeing the data. With these two capabilities, we are no longer flying blind. We can now start diagnosing why things are failing. In our next topic, we will take this foundation and apply it to the systematic approach for troubleshooting both application and cluster level failure. Thank you.